Hey there, and welcome back to section 7.2 on spans. In this video, we're going to begin subsection 7.2.2, spans viewed geometrically in R3, and in particular, we're going to do example 7.2.4. So before we begin, we should just take stock of what this sentence says here, and that is, in order to interpret spans geometrically, we're going to draw all vectors in standard position, which means, as you remember from your unit on vectors, we're going to draw them starting at the origin. Okay, so let's begin with example 7.2.4, and we're asked in each of the following situations to give a geometric description of the span of the given collection of vectors. So with part A, the span of the zero vector, we have to remember what span means, and span is the collection of all vectors, or in three-dimensional space, that can be expressed as a linear combination of the collection of generators. And our linear combination of a single vector, we have to remember, is a scalar multiple of that vector for any scalar in R. So if we take a look here, well, we can simplify this. Any scalar times the zero vector is going to give me 0. So that is the set of all vectors in R3 such that W is equal to the 0 vector. Well, there's only one vector in R3 that's equal to the 0 vector, and that is the 0 vector. So the span of the 0 vector actually is a single vector, and if we plot that vector in standard position, the 0 vector is plotted at a point, it is the point of the origin. So the span of the 0 vector, actually in any space, but in R3 and three-dimensional space in particular, is the point of the origin. So let's go and take a look at B. B is now asking us, well, what if we have the span of a single vector, but that vector is non-zero? So that vector u is given to us in the diagram here as a potential example. And the span of a vector u is still the set of all vectors that are linear combinations of that vector, so that means a scalar multiple. So it's a set of all vectors w that are scalar multiples of u for any scalar in R. It's a set of all possible linear combinations of this sort. And you actually know what this is. If we were to rename things, let's say that I chose to let my vector be called d instead of u. And instead of a scalar being called a, why don't I replace that with t? In other words, I could say that this is the set of all vectors w in R3 such that w is equal to t times d for any t in R. Does that look more familiar? No? Maybe I should spell it out a little bit more even. W is in three-dimensional space, so that means I can write it as the vector x, y, z, such that x, y, z is a scalar multiple of d. Well, d has components d1, d2, d3, let's say, and this is for any t in R. Now that really should start to look familiar. That is exactly the equation of a line. And it's not just any line. It's a line where the point that we can see on that line, right, that point is not there. In other words, it is potentially written as the 0 vector, right? 0 plus t times d1, d2, d3. So this is exactly a line through the origin in three-dimensional space. Now, that makes perfect sense. If we think about this geometrically from another standpoint, we are looking here at all multiples of this vector u, yes? W, our span, collects together all scalar multiples of this vector. Well, let's just draw some scalar multiples in. If I drew another multiple, well, that multiple has to be parallel. We've seen that vectors are parallel if and only if they are multiples of each other. So I might have a vector there drawn in standard position. It is going to look something like this. If I just keep on drawing vectors that are parallel to u, drawn in standard position, they end up, if I draw all possible of them, obviously I can't, but the more and more of them that I draw, it becomes clearer and clearer that those vectors are indeed forming a line through the origin. So the span of a single non-zero vector in R3 is the line through the origin. C, the span of two vectors which are non-parallel in three-dimensional space. You may already be guessing what this is going to look like. Well, let's write it out so that we have no guesswork. The span of two vectors is the set of all vectors W, or in three-dimensional space, such that W may be written as a linear combination of those two vectors, so that A and B, the coefficients, can be any scalars that we so choose. Right, so that if it's not obvious, we'll do a little relabeling and a little rewriting of things like we did in part B. What if we had called U a vector D1, and if we had called V instead a vector D2? And instead of using A and B as our coefficients, what if we'd used S and T for any S and T in R? Well, then we have, again, the set of all W in R3 such that W can be written as S times D1 plus T times D2 for any S and T in R. And if that's not driving it home, let me spell it out again like the last example. W is a vector in R3, so it's the set of any vectors, of all vectors, x, y, and z, such that x, y, and z, I'm going to insert the 0 vector because I can. 0, 0, 0 plus s times d11, d12, d13 plus t times d21, d22, d23, and that is for any S and T in R. That is the span of these two non-zero vectors, and so you should recognize all of this as the vector equation of a plane through the origin in three-dimensional space. So let us go and draw that as well. That plane would be the plane containing these vectors. So in fact, the span, all of these spans are things that you have seen before. They are being described now through the language of linear combinations, which actually is how we described them before, but we did not name it that way. In the next video, we're going to explore a little bit more the possibilities of other collections of vectors without necessarily these same kinds of criteria, constraints applied.